Hello, welcome back to a lecture about infinite series. This is part of lecture number 11, I believe. And in this lecture, we're going to solve problems. We start solving problems from previous lecture, but we couldn't finish. Right now, we were doing this problem, and then the video ended. So here I'm going to find the limit using uh, the root property. So to find the limit using root property, we're going to put the root as it is, and then we find limit as n goes to infinity of 16n squared divided by 2n squared plus limit as n goes to infinity of 3n over 2n squared. That would be equals to limit as n goes to infinity of 8 plus limit as n goes to infinity of 3 divided by 2n. So the limit of this is going to be equal to 0 raised on 1 over n. So limit of 1 over n, 3 would be pulled out. So that could be written in a different way. Limit as n goes to infinity of 8 plus 3 over 2 limit as n goes to infinity of 1 over n. This is cubic root here, cubic root, cubic root. So the limit of 8 is going to be 8. Limit of this one is going to be 0. So then I'm going to get cubic root of 8, and that should be equals to 2. So in this theorem, we want to discuss about if I have a sequence S of n, and limit of this sequence is equal to L. And then there is a function that is continuous at the result of the limit. So then when we take the limit of that function, a function of S of n of that sequence, we get f of L. Okay, we will discuss this in details in this problem. So here, say this is my sequence S of n. So it's equals to 2 over n plus 3. We want to find the limit as n goes to infinity of this sequence. So we are going to get 3 because limit of this one is 0, limit of 3 is 3. Okay, now let's do what the theorem says. So now let's find the limit of f of S of n according to the theorem. This should be equals to f of capital L. So that means limit of, so here this is consider that to be your f. Okay, so limit of L 2 over n plus 3 as n goes to infinity, this should be equals to ln of 3. Okay, so this is what the theorem was talking about. So identify the related function of this. So the related function f of x, that should be equals to x over e to the x. So wherever I have n, I substituted n for x. So theorem. So let S of n be a sequence, and then the related function of that sequence is f. If limit of f of x is equal to L, that means the limit of S of n would also be equal to L. So we are using the related function method to determine whether this sequence here converges. So the related function of this would be equals to 3x squared plus 5x minus 2 over 6x squared minus 6x plus 5. So limit as x goes to infinity of this function 3x squared plus 5x minus 2 over 6x squared minus 6x plus 5. So limit of a rational function, this rational function as x goes to infinity, the behavior of this rational function would be determined by the two leading terms, which is these two terms here, which is 3x squared over 3x squared over 6x squared. That means the limit is going to be 1/2, because x squared and x squared cancels out. So we are going to discuss about the squeeze theorem. If I have a sub n, b sub n, and s sub n, these are sequences. Sequence b sub n is above, and sequence a sub n is below. In the middle, we have s of n. If limit of a sub n, the function below, equals to b sub n, a function above, and the result is L, that means the function in the middle would have the same limit, which is equal to L. So right now we want to use a squeeze theorem to evaluate this sequence, or to evaluate the limit of this sequence. So here I have -1 raised to the power of n over n. We think about, so the hardest part usually in a squeeze theorem is to come up with the function that will bind your function, or will sandwich your function. So this right now, this is easy for this type of function. Sometimes it could be hard. So we think of a function that will bind this two function, or will sandwich this function. So it's going to be -1 over n. If we take the limit of -1 over n as n goes to infinity, this must be equals to limit as n goes to infinity of 1 over n, and that should be equals to 0. That means the limit of this function here is going to be equal to 0. So here we're going to talk about geometrical sequence. So the geometrical sequence S of n is equal to r raised to the power of n, where r here is a real number. So this one converges if r is in between -1 and 1. It converges also if r is equal to 1, and it diverges if r is greater than 1. So this function here, I have r equals to 4 over 3 greater than 1. That means it diverges according to the theorem. Here I have r equals to 3 over 4. According to the theorem, this function here converges. So we want to talk about a sequence S of n which is bounded above if every term of that sequence is less than or equal to some number m. Similarly, a sequence S of n would be bounded below if every term of the sequence is greater than or equal to a number small letter m. So this is a function that is bounded above. This is a function that is bounded, or this is a sequence that is bounded below. Okay. So determine a sequence is bounded from above or from below. So this sequence here, S of n, so we see this sequence is going to be, we can actually make 3, we divide by n, all up and down. So here I'm going to have 1, here I'm going to have 2 over n. So this function here, or this sequence here, is bounded above this function because this converges to 3. All right, it will never reach 3, but it converges to 3. And as we know, this function, this sequence here is also bounded. It can never be equal to 0. Okay. This sequence here can never be equal to 1. All right, it can never be equal to 1. It has to always be equal to 1. It has to be greater than 1 all the time. But it goes, it diverges. So it is bounded below. This is bounded from above and from below. But this function here, or this sequence here, is not bounded at all. Okay, so right now we're going to talk about an increasing sequence. Sequence is said to be increasing if S of n less than or equal to S of n plus 1. So that means S of n plus 1, the term of the sequence, this term is always greater than this term. This is going to be an increasing sequence. Well, if S of n sometime is equal or sometime is greater than S of n, then we call that non-decreasing sequence. Similarly, if S of n is always greater than S of n plus 1, that means this is a decreasing. Okay, and then this is how you you find a decreasing sequence, and this is how you examine an increasing sequence. All right.